Welcome to this explainer. Today, we're literally popping the hood on modern electric vehicles to see exactly what makes them tick. I mean, have you ever wondered what is actually going on beneath you when you just silently glide away from a stoplight? The architecture of these machines is a massive, and I mean massive, departure from the gas-guzzling engines we've relied on for over a century. It's completely reshaping how we think about transportation. So what actually happens when you press the pedal of an EV? It seems super simple, right? You press down and boom, you go. But that instant rush of power is actually a highly sophisticated, elegantly orchestrated dance of chemistry, software, and advanced engineering. And hey, before we get into it, if you want to keep unraveling the incredible tech that's shaping our future, definitely hit that subscribe button to our channel. We're all about taking complex systems and making them totally accessible for you. Okay, let's dive into this anatomical tour from the ground up. We're going to cover Section 1, the skateboard foundation. Section 2, the heart, which is the EV batteries. Section 3, the brains, or power electronics. Section 4, the muscle of the electric motors. And finally, Section 5, we'll get into regenerative braking explained.
All right, starting things off with Section 1, the skateboard foundation, or the EV base. To really wrap our heads around an electric vehicle, we got to start at the very bottom. For decades, traditional internal combustion cars were built around this bulky engine, a really long exhaust system, and a hugely complex transmission. EVs completely flipped this script. Enter the skateboard platform. It gets its name because, well, quite literally, it looks like a giant skateboard. It's this incredibly flat base that houses the heavy battery pack right smack in the middle, with the electric motors and electronic components neatly tucked at the ends near the wheels. And because this layout is so low to the ground and totally self-contained, automakers can basically snap any type of body right on top of it. A compact city car, a luxury sedan, or even a heavy-duty pickup truck can all share the exact same underlying skateboard. This elegant solution drastically cuts down development time and engineering costs compared to, redesigning a complex gas-powered chassis every single time you want to release a new car.
Moving right along to Section 2, the heart, our EV batteries, where all that energy is stored.
Now that we have our solid, flat foundation, let's look at the component that makes up the bulk of that skateboard, the true beating heart of the electric vehicle. When you think of a car battery, you might be picturing one massive, heavy block of lead. But an EV traction battery is way more intricate. Think about the standard AA batteries you put in your television remote. Now imagine wiring thousands of those together. That's essentially what's happening here. The journey starts with individual battery cells. Some look like small cylinders, some are rigid and rectangular, and others are soft pouches. These individual cells are grouped together into modules. Then, several of these modules are linked up inside a massive protective casing to create the high-voltage battery pack that actually powers the car.
Now, what's truly fascinating is how automakers choose the actual chemistry inside those cells. Today, the industry relies heavily on two main variations of lithium-ion technology. On one side, we have NMC, which stands for nickel, manganese, cobalt. This chemistry packs a massive punch. It offers incredibly high energy density, meaning you get maximum driving range for a given weight. On the flip side, we have LFP, or lithium iron phosphate. While LFP cells are slightly larger and heavier for the exact same amount of energy, they are remarkably stable, highly resistant to overheating, and they completely avoid rare and costly metals like cobalt. Automakers have to carefully balance these trade-offs, right? So they often use LFP for base models to lower costs, and NMC for those high-performance or super long-range versions.
But here's the thing. These batteries can't just operate completely on their own. They require a vigilant guardian, which is the Battery Management System, or BMS. Batteries, believe it or not, are kind of like us. They're happiest at a nice, comfortable room temperature. If they get too hot under heavy acceleration, or too cold in freezing winter weather, their performance totally drops off. The BMS is a highly advanced software suite that is constantly monitoring every single cell. If the pack is getting too warm, the BMS circulates liquid coolant. If it's too cold, it uses energy to warm the pack right up. Actually, scratch that. It's more like a thermostat and a bodyguard combined. And this constant management is exactly why modern EV batteries can last for years and years of daily driving without degrading.
Okay, Section 3, the brains, or power electronics. This is all about directing the flow.
So, let's recap. We have a flat chassis, and we have a massive temperature-controlled battery pack storing chemical energy as direct current, or DC electricity. But here is the catch. The wheels don't turn on DC power.
we need to translate that energy. So the crucial point is, without an inverter, your electric vehicle would literally just be a very expensive, very heavy paperweight. The battery speaks one language, direct current, while the electric motor speaks a totally different language, alternating current, or AC. The inverter acts as the high-speed translator between the two. It sits right inside the power electronics module and handles the massive flow of energy rushing out of that battery pack.
And the way it does this is absolutely fascinating. As the DC power flows in from the battery, the inverter uses specialized power transistors acting as high-speed switches. It rapidly slices and dices that steady stream of DC electricity, a really cool technique known as pulse width modulation. By turning the power on and off incredibly fast, it perfectly mimics a smooth alternating wave of energy. This beautifully tailored AC wave is then fed directly into the motor.
Which brings us to Section 4, the muscle. The electric motors turning all that energy into actual motion.
We've successfully routed our energy and we've converted it into a usable wave. Now it's time to introduce the muscle. If you've ever driven a traditional gas-powered car, you know it has to constantly shift gears as you speed up. That's because combustion engines only make good power in a really narrow band of engine speeds. If you don't shift, the engine just screams without giving you any more speed. Electric motors, they completely eliminate this problem. They have what engineers call a broad, flat torque curve. This means an EV motor can deliver its absolute maximum pulling power instantly, like the exact millisecond you press the pedal, and it maintains that power across a massive range of speeds. Because of this crazy efficiency, EVs don't need complex, heavy multi-gear transmissions. A simple, single-speed transmission does the job flawlessly, giving you that famous, completely uninterrupted, spaceship-like acceleration. And the motors themselves? They are evolving so fast. For a long time, the industry standard has been the radial flux motor. In this design, the magnetic forces travel outward from the center, kind of like the spokes of a bicycle wheel. They are highly efficient and really easy to manufacture. But lately, engineers have been pushing the boundaries with what's called axial flux motors. Instead of a cylinder, imagine two facing disks spinning parallel to each other. This layout creates a much larger magnetic surface area in a flatter, significantly lighter package. It provides absolutely massive power density, meaning you get supercar levels of horsepower out of a motor that is just a fraction of the weight and a fraction of the size. It's a real game changer.
Finally, Section 5, regenerative braking explained, or how EVs recycle energy.
Making the car go fast is awesome, for sure. But eventually, you gotta stop. In a traditional car, when you hit the brakes, friction pads clamp down hard on metal rotors. All the kinetic energy of your heavy, moving car is violently turned into heat, and that energy is just wasted forever into the atmosphere. To understand how EVs pull off their greatest magic trick to fix this, let's first look at the normal flow of energy. When you are accelerating or cruising along, you are drawing energy from the batteries. The energy travels from the pack through the inverter, where it becomes AC power, and down into the motor. The motor uses that electrical energy to physically spin the wheels. It's a straight-up, one-way street of power consumption.
But, and this brilliantly illustrates the magic of an EV, that all changes the exact moment you lift your foot off the accelerator. The entire system instantly goes into reverse. The electric circuits essentially cut the power feed to the motor. But because your heavy car is still physically rolling forward, its forward momentum keeps the wheels turning. Now the spinning wheels are physically forcing the motor to rotate. And because of the fundamental laws of electromagnetism, an electric motor running in reverse acts as an electric generator. So as your kinetic energy spins the motor, it creates new AC electricity. This physical resistance is actually what slows your car down. Often it works so well that you rarely even need to touch the physical brake pedal. That newly generated AC power flows back up to the inverter, which flips it back into DC power and then feeds it directly back into the battery pack. You are literally recapturing the energy you previously used to get moving, storing it, and extending your vehicle's driving range simply by slowing down. It is a brilliant, closed-loop system of elegant efficiency.
So from the incredibly flexible skateboard chassis at the base, up through the meticulously managed battery packs, those high-speed inverters, the instant torque of the motors, and the brilliant recycling of regenerative braking, an electric vehicle is truly a masterpiece of modern design. It completely removes the thousands of exploding, friction-heavy moving parts of a gas engine and replaces them with a quiet, efficient flow of electrons. But you know what the craziest part is? This technology is still in its infancy. With breakthroughs like lighter axial flux motors and the promise of upcoming solid-state batteries, the efficiency and power of these machines are only going to increase from here.
So as these rapid technological leaps continue to hit the streets, it leaves us all with one final thought. What will the future of driving look like a decade from now? Thanks so much for joining me on this explainer, and we will see you next time.